Hello and welcome to another general chemistry video. Today we will be finding out quantum numbers using electronic configuration. So remember, electronic configuration really is the location of the last placed electron within an atom. Now I'm stressing the last placed electron because when we're talking about electronic configuration in this sense, using it to find quantum numbers, we really just care about that last portion that we found. For example, in cobalt, we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d7, right? And this is the electronic configuration for cobalt. However, if we're already adding electrons to the 3d7 shell or the 3d shell, we can assume that everything that came before it is already full. Otherwise, we would not be adding electrons to this shell. So we can see that everything that comes before cobalt is already full. That's why this last shell is really just the most important. Now, if you look to the left, we can see a handy chart that I drew here. That, let's expand this before, 3d7 can actually be used to figure out our quantum numbers. And remember, our quantum numbers are n, l, ml, and ms. Now, let me go up right here. Remember that what is the energy level of cobalt? Well, we can see that because of here, it's on the fourth row and in the D block, which means we have to subtract one from the period, and we find that that has a 3 energy level, or it's in the third energy level. Same thing here. In here, it shows that this is also on the third energy level, so we can see that the N, which stands for energy level, is equal to 3. So we just plug this in for this quantum number. So remember the chart that I showed you last time where the S, P, D, F block is equal to 0, 1, 2, 3 respectively, right? So we got 0, 1, 2, 3. So that's why, because this is on the D block, it has an L of 2. Now, ML is a little bit trickier and MS is also a little trickier. But one way I do like to find this is by using the periodic table instead of this electron configuration. So when I do this with the periodic table, I like to split each block in half. Right? And you can see that we can nicely split each block in half. And I won't do this for the F portion, but notice how that each block is equally split in half. Now remember, this is the S, and the S block has an L value of 0. Remember that this L value causes the ML value to be from negative L to positive L. What does this mean? Well, this block goes from negative 0 to positive 0. Same thing here, it goes from negative 1, 0, positive 1, and then repeats negative 1, 0, positive 1. Same thing here, negative 2, negative 1, 0, 1, 2, negative 2, negative 1, 0, 1, 2, right? And so we can see now that cobalt actually falls within that negative 1 shell, or negative 1 orbital. That's what we're going to put for Ml. And for Ms, we can see, because it's on the right side of the half, we input a value of negative 1/2. If it's on the left side, we'll input a value of positive 1/2. So if it's on the left, positive. If it's on the right, negative. Left, positive. Right, negative. Right? Pretty self-explanatory. So that means Ms is equal to negative 1/2. And these are actually our quantum numbers for cobalt, right? And this is standard ground state cobalt. Now, how do we actually find the ML and MS using this number? Well, a lot of it has to come down with practice, but you can also think of it as this way. If the number is typically a bigger number, if it's a bigger number, then MS is going to be equal to negative 1/2, right? If we have to move more spaces within this block, we can figure out that most likely it's going to be on this latter half, right? But typically what I like to do is I like to just use these first two using electronic configuration, EC, and these last two, I use a periodic table. So really it's a combination of both. Now, one last problem for you to try out, and I'll tell you the answer to this. All right, so find me the quantum numbers and the electronic configuration of beryllium, ground state beryllium. Well, let's start with the electronic configuration. The electronic configuration is 1s2, 2s2, right? You can see, right, 1s2, and then 2s beryllium, right? So this is right. So remember, we're only considering this last part, or the latter portion of it. So NL, ML, and MS. So N would be 2. Remember that S is equal to 0. ML can go from negative L to positive L, but since L is 0, ML is also 0. And let's go all the way up to the periodic table. Is it on the left half or on the right half of this S block? Well, because it's on the right half, we're also going to figure out that MS is equal to negative 1/2. So that is the quantum numbers using electronic configuration and the periodic table. So now it is your turn to practice. I want you to pause the video right now and find the electronic configuration and the quantum numbers for these atoms. Now pause the video now, try it out for yourself, and then continue with the video when you're done. All right, so you should be done at this point, and if not, try this again. But here are the quantum numbers. Notice how I do not need the electronic configuration, simply because if our quantum numbers are right, then that also means that our electronic configuration is right, because we got these first two numbers from the electronic configuration. So that was kind of a sneaky trick on my end to help you guys get more practice. But that comes to the end of this video. If you have any more questions, just rewatch your video or ask your peer leader. I'm sure they will be happy to help you. We will see you guys in the next one.